Okay, thank you very much for giving me this opportunity to come here and present my talk. My name is İsmail Boztosun. I am from Akdeniz University, but also I'm partially at TÜBİTAK Fundamental Sciences Institute, also at the Turkish Accelerator and Research Laboratory. I mean, such summer schools are very important. I mean, you are at the beginning of your career. Therefore, it is very important to learn the basics of the science as well as also the networking. My best friends are from the ones that I attended the summer schools, because it is a kind of networking from each of you from different parts of Turkey or even the world at different universities. Therefore, in the future, if you consider 10 years later, I mean, each one will be at different places. Therefore, it is important that you keep this networking, actually. Also, please also stop me if you don't understand anything. I can also explain in Turkish. I mean, don't worry. Now, today, I will be giving 3 lectures in a row. These are the basics of nuclear physics from a personal view. Therefore, I always, at the beginning of my lectures, not only the nuclear physics, but also modern physics lectures, I always put this figure. I mean, we in quantum chemistry, in quantum physics, and also in modern physics, we always solve this either square web or barrier problems. I mean, what is the physics? Why do we solve these problems? Why do we have so much, so sophisticated, complicated mathematical tools to use such equations? I mean, I hope at the end of this lecture, I mean, you will be understanding this, why we are doing this, solving such barrier or well problems. I mean, in the first lecture, I will be giving you the review of nuclear structure, basically what is nucleus. Because if you see around, everything, including you, me, even this light or this water, it has this atomic structure. Basically, atomic bondings, either covalent or ionic bindings. And inside this atom, we have this nucleus, protons and neutrons. Therefore, in the second lecture, I will do briefly the reactions, what is scattering, what is reaction, the differences, and how we describe them, and also new topics like exotic nuclei, etc. In the third lecture in the afternoon, I will be briefly providing you the information basics of radioactivity, basically, and I will end. Therefore, today we will be spending time together. I hope you will enjoy. I mean, these are the basic books on nuclear physics and also some advanced one. I mean, if you are going to specialize on nuclear structure and reactions, definitely you should be following one of these books. I mean, let's start with the modern physics. By the end of 19th century, most scientists believed that the laws of physics were all known. Therefore, nothing left actually in physics by the end of 19th century. Because the planetary motion was understood by using Newton's and Kepler's law. And also the laws of electricity and magnetism were known. These are well-known Maxwell's equations in the bottom. These are shown. Also, the conservation principles were established, like the conservation of mass, energy, and charge, etc. Therefore, it was claimed that nothing left, actually. Therefore, there is no point to read the physics in 19th century. Then what happened is very interesting. The problem was if you consider an atom, this is the nucleus made up of neutrons and protons, and electrons are the ball. Therefore, the classical physics couldn't explain the stationary states of of these electrons. But normally, in classical physics, I mean, if you consider a particle evolving, it should lose the energy and fall into the center. Whereas in atom, it doesn't happen and follows the... Oh, tamam, süpersin. Şu mu olacak? Therefore, this was the main problem. Then what happened is what we call modern physics or modern era of 20th century. That is discovery of black body radiation, photoelectric effect, and the Compton scattering. Therefore, what we obtained is quantization or discrete levels of energy and wave particle duality, as well as the concepts of modern physics or quantum physics. This is like opened an era, and now in modern technology, whatever we see here is related to this modern physics, including this projector and computer and others. Now, this is basics of nucleus and its properties. There are internal properties like spin, parity, magnetic electric moments, or there are external. When you see it physically, I mean, you describe first external properties like charge, mass, size, and shape. Therefore, this is atom in the center. This is nucleus. It is denoted by like this, X. Z is the mass atomic number or proton number, N is neutron number, A is the mass number, which is the sum of Z plus N. This is called actually central protons and neutrons, commonly called nucleon. Mostly you should hear this as nucleon. We don't say proton or neutron, but we call them nucleon. If you see this chart, this is, let me see, neutron number versus proton number. This is line of stability or value of stability, it is called. Therefore, protons and neutrons are located here all over up to proton numbers 92, up to uranium, basically. Therefore, we call them nuclide element with given Z and N. We call them isotope element with the same Z but different N. Call them isoton element with the same N but different Z. And isobar element with the same A. And also mostly in nuclear medicine.
İsmail Bey, bölüyorum, çok üzgünüm ama ekran paylaşımı gelmedi. Online'dakiler olarak şu an takip edemiyoruz sizi.
Ekran paylaşımı, pardon, kusura bakmayın. Paylaşım mı yapacağız burada? Şu an tamam mı?
Evet, şu an tamam. Çok teşekkürler.
Tamam, peki. Therefore, isomers element in metastable or very long-lived actually state. Therefore, what we identify as a nucleus is by looking at its proton number. Therefore, I mean, the atomic number or proton number is like a surname of a nucleus. I mean, I am sure in Ege University there are lots of people called İsmail, but when you specify İsmail Boztosun, it is like, yeah, like pointing me, more or less. Therefore, it is important to know these isotopes, isobars, isotones, and others for future applications. Now, if you look at the charge of a nucleus, protons, the charge is positive due to protons. It has positive charge, and it is exactly same as electrons charge with different sign. Neutrons have zero charge, it's chargeless, neutral, and symbolically we show it like this. About the mass, I mean, it is the nuclear or atomic masses are expressed in atomic mass units. It is denoted by U. As a definition, it is 1/12 of neutral mass of 12 carbon. And it is, in terms of energy, it is 931.541 MeV over C square from Einstein's relation. And we know that nucleus mass is always smaller than individual sums of its constituents, like protons and neutrons. Therefore, it is called mass defect. If you multiply it by C square, it is in terms of energy, and it's called binding energy of a nucleus. Binding energy of a nucleus is either to keep a nucleus together or apart them its constituents. Therefore, the binding energy concept is very, very important. Please also remember this expression and also this Einstein's relations. Regarding the masses of proton, neutron, and electron, in terms of atomic mass unit, please don't forget this, the charge, mass, and spin, because these are fermions, you see, and these obey the Pauli exclusion principle, and also parity. I mean, please don't forget this. Regarding the size, what is the size of a nucleus? I mean, we know that you are already aware of atoms in the size of angstrom, but the size of a nucleus is expressed in Fermis or femtometers. That's 10 to the minus 15 meters. Therefore, it is like, compared to the atomic size, it is 10 to the 5 smaller than an atom. And how we define the size or radius of a nucleus, it is 1/3 of mass number. It is proportional to. Therefore, please also remember this, so that you know, when you need to calculate the radius of a nucleus, you need definitely this expression. Therefore, it is like, if you consider an atom like this is the electron, and at the center of a football pitch, it's like this ball, it's like a nucleus. Therefore, actually, we are, or matter is a completely empty space, actually. We are almost empty, full of empty, actually. Therefore, these are, please calculate the radius of these nuclei to get just expressions to know. Then we know that protons are positively charged particles. Therefore, it should repel each other. Therefore, how a nucleus form and keep it together, the protons. Therefore, this is the solution. That's what's called this nuclear force. It is a very short range, and we have also Coulomb repulsion. Therefore, the resulting potential between protons or in a nucleus is something like this. There is an attractive part that keeps nucleus together, and there is a repulsive part. Therefore, it is like dual type potential, both positive and negative parts. And this is very important for classical radioactivity applications. I mean, if this is what is called Coulomb barrier, it is like proportional to the charges of two nuclei or two charged particles with R. Now you know that it is proportional to the 1/3 of mass number. Okay, but if we have you see, a nucleus made up of protons and neutrons, basically it should have some physical properties like mass, charge, etc., but also density. How does a nucleus look like? Now, we do electron scattering experiments and charged particle experiments, and we observe that a nucleus is like a hard core up to 4 or 5 Fermis. It is impenetrable. It is so hard. It is impossible to get in. But then in the surface part, it drops exponentially. Therefore, one can penetrate into the up to a point of nucleus. Therefore, this is like called surface thickness. We can express this the density of a nucleus with such Fermi formulation. It is called Fermi formulation. It's a kind of exponential fall. Therefore, rho r could be expressed like this. The density, the half of the value of the half of the density is called mean radius, average radius. Therefore, this radius is, we know that proportional to 1/3 of mass number. And if we look at all nuclei, from except very light ones like hydrogen or helium and others, they almost show the same shape for all nuclei, from carbon to uranium. They almost present the same shape as the exponential fall, or Fermi formulation. I mean, this is, of course, an empirical approximation or empirical way of presenting a formula for the charge or mass density. Now, this comes to the nuclear force concept. I mean, what is this? How a nucleus stay together, although these protons repel each other so strongly. Imagine Coulomb force between two protons. I mean, they repel each other so huge that it is impossible to keep them together. That's why we have this nuclear force concept. It is not known from the first principle. I mean, like gravitational force or other electromagnetic forces, but we predict it can be estimated from nucleon-nucleon interaction, properties of deuterium, or curve of binding energy per nucleon. Therefore, we know that it is very short range. At the very short distances, it is extremely attractive. You see, I mean, it's like a very, very attractive potential at negative sides. At very short distance, like 0.5 Fermi, it is extremely repulsive. It's very positive. So that two nucleons, I mean, two protons or two neutrons, or a proton and a neutron cannot touch each other. You see, this is resulting potential. It has charge symmetry, it has spin dependent, and because nucleons are fermions, as you know, And we know that neutron-proton force is stronger than neutron-neutron and proton-proton force. Therefore, this is the nucleon-nucleon force. You should at least have some idea what it is. That's why I put. Therefore, so far, I mean, these are the basics. Nuclear physics could be separated in three parts: nuclear structure, nuclear reactions, and radioactivity, as well as resonances together. When we say nuclear structure, there are three different models. I will be briefly explaining now. In the next lecture, nuclear reactions, and finally, radioactivity. But we know that in nuclear physics, there is no complete theory to fully describe a nucleus. There is no theory, I mean, fully describing the nuclear physics. Therefore, it is still important area to study. Now, first model in nuclear structure is called liquid drop model. I mean, we look at nucleus like this first physically and try to describe it. Therefore, what we do there as nuclei regard as collection of neutrons and protons forming a droplet of incompressible fluid. Therefore, this is why we call them liquid drop model. And it is a kind of semi-empirical mass formula derived from the experimental values. And there is this volume term, surface term, Coulomb term, and others. Therefore, each one described here, please have a look at it. And therefore, it is overall, it accounts for all trend of binding energies and correctly predicts masses of most nuclei. What we mean is this is the binding energy per nucleon here. This is mass number. This is the binding energy. If we draw this, we get this curve. For light ones, small ones, there are peaks, but then it becomes almost constant. Therefore, there are peaks here. You see 4, 8, 12, 16, 20. There are some resonance type peaks. It increases. Therefore, this semi liquid drop model or semi-empirical mass formula doesn't account for extra binding energies at these numbers. These correspond to the magic numbers, these are called. If your neutron and proton numbers equal to one of these, you have a higher binding energy. And this liquid drop model cannot explain these magic numbers or the increase of binding energy at these specific numbers. Also, it doesn't explain abundance peaks, why some nuclei are in the universe more than the others. It cannot explain. For even nuclei, it cannot explain why they are more stable than odd nuclei. Also, it doesn't explain excited state spin parity, energies of low-lying excited states, etc. Therefore, we need a refined model to explain these experimental or observational facts. It is called shell model. I mean, in your background, I mean, have you seen these models like liquid drop model, shell model, and others? Do you know them? I mean, is it too basic or advanced so that I can explain in detail if you don't understand? And yeah, please. Tabii. Ya buradaki şimdi bir şöyle düşünün. Çevremizdeki gördüğümüz her şey iyonik ya da kovalent bağlar ya da metalik bağlar yapmış atomlardan oluşuyor. Tamam mı? Her şey yani siz, ben dahil, bu tahta dahil. Yani dolayısıyla bu bağlar, bu atomik yapı, atom fiziğinin alanı. Onun içerisine girdiğiniz zaman çekirdek var. Çekirdek dediğimiz şey proton nükleus, yani proton nötronlardan oluşuyor. Tamam. Şimdi bu protonlar arasında müthiş bir itme gücü var. Coulomb yasasına göre. Ters kare kanunu, yani Z1 Z2 bölü R kare diye düşünürseniz, R ne kadar küçülürse şiddeti o kadar artıyor. Peki bu protonlar nasıl bir arada kalıyor nötronlarla? Dolayısıyla orada bir nükleer konsepti anlattık. Kuvvet var. Nükleer kuvvet bunları bir arada tutuyor. Tamam. Tabii şimdi bu çekirdeği bir arada tutan ya da bunu parçalamak için gerekli olan enerjiye bağlanma enerjisi diyoruz. Binding enerji. Şu B var ya, pardon. Şu B. Binding enerji, bağlanma enerjisi. Tamam. Şimdi dolayısıyla ilk akla gelen şey, fiziki olarak şuna bakıp tanımlıyoruz. Diyoruz ki boyu şu, çapı bu, yükü bu vesaire, kütlesi bu. Bu fiziki dış özellikler. Bunun parçalamak için ya da bir arada tutmak için gerekli enerji, bağlanma enerjisini nasıl hesaplarız diyoruz. Bunu da bir genel trend olarak baktığınız zaman diyorsunuz ki nükleon başına bağlanma enerjisini böyle çizdiriyorsunuz. Şurada uranyum atomu 92 tane stabil var. Tamam mı? Proton sayısı 1 olan, şimdi proton ya da hidrojen, 2 helyum, lityum vesaire, 6 karbon, işte 92'de uranyum. Bunların izotopları da var tabii. Yoksa bunları böyle çizdirdiğiniz zaman şurada bir trend görüyorsunuz. Diyorsunuz ki bunlar binding enerji, bağlanma enerjisi, nükleon başına A. Hemen hemen sabit. Ama şurada bir uyumsuzluk var diyorsunuz. Bazı değerlerde böyle artışlar var. Miktar. Bunlar işte Magic'ten sihirli sayılar deniyor. Nötron ya da proton sayımız bunlardan birine eşitse bir anda daha karanlık, daha yüksek bağlanma enerjisine sahipsiniz. Tamam mı? Şimdi bunu açıklayamıyor ama genel ortalama bağlanma enerjisini açıklıyor. Bir sıvı damlası gibi düşünüyor yani çekirdek. Yani bir su damlasını düşünün. Aynı bunun gibi. Merkezde diyor çok şiddetli bağlı, yüzeylerde diyor düşüyor. Dolayısıyla bunu da şöyle açıklıyor. Diyor ki böyle bir şey varsa diyor, yani ilk terim aklımıza ilk gelen hacmi, yani hacim terimi ciddi katkıda bulunuyor. Yüzey terimi onu azaltıyor. Blok terimi biraz daha azaltıyor. Eğri. Dolayısıyla mikron başına bağlanma enerjisi bakın şöyle bir şeye gidiyor. Bunların her birinin değerleri de burada veriliyor. Buna ampirik bir yaklaşım deniyor. Deneysel sonucum var ve elde ettiğim bir teori var. Sonuç. Bu bağlanma enerjisini vesaireyi, kütleyi açıklıyor ama şunları açıklayamıyor. Bu spiniymiş, uyarılmış durumlarmış. Mesela çift proton, çift nötron. Mesela karbon diyelim. 6 proton, 6 nötronu var. Karbon 12, niye? Karbon 11 diyelim. 6 proton, 5 nötron. Karbon 12'nin karbon 11'den niye daha çok olduğunu açıklayamıyor. Çift çekirdekler, yani çift proton, çift nötrona sahip olanlar bu evrende çok daha fazla. Şimdi bu konuların ardından diyelim uyarılmış durumlar, spini, haritesi. Bunlar niye önemli? Çünkü nükleer tıpta ya da radyolojide radyoaktivite, yani bir şeyin bozulmasına baktığınız zaman diyelim şu enerji seviyesine, bu enerji seviyesine bir foton yayınlayacak, gamma ışını yayınlayacak ya da bir alfa ya da bir elektron yayınlayacak. Dolayısıyla o ya görüntülemede, diagnoz etmede, teşhiste ya da tedavide, tamam mı, kullanılacak. Dolayısıyla o uyarılmış enerji seviyesini bilmeniz çok önemli. Yani oradaki diyelim tümörün vesairenin özellikleri ne kadar nüfuz edebileceği, ortalama ne kadar serbest yol alabileceği o bilgiler. O yüzden uyarılmış durumları falan bilmek gerekiyor. O yüzden hani bu ilk 4-3 dersi çok temel seviyede koymaya çalıştık ki, ama her şeyi sorabilirsiniz yani. Yine açıklarız böyle Türkçesini. Ne güzel, aferin bak cesaretin için. Neydi adınız? Eygi. Ya niye böyle zor isimler koyuyorlar? Eygi. Tamam Eygi, bak çok güzel. Lütfen sor, tamam mı? Yani hiç böyle çekinmeyin lütfen. Açıklanamıyor işte. Sizin gibi gençleri bekliyoruz yani. Ama anlatacağım şimdi, tamam mı? Yok, yok. Açıklamıyorum. Ya tabii şimdi yok, açıklıyoruz şu an. Shell modelden dolayı açıklıyoruz. Şimdi tekrar İngilizceye mi geçeyim? Ege. Tamam. Okay. Now these are the actually evidence of shell effects. You see here, I mean, we see, for example, abundance curve of nuclei. I mean, some nuclei or some elements are in the universe more than others. Therefore, we see those peaks or some separation energy. Some nuclei have neutron or proton separation energies higher than the others. Normally, I mean, it is in the 10 to the minus 15 meters. You expect all the same, but these are different than each other. Or some neutron capture cross section and the value of stability. Some stable isotopes are not well explained by the other models. Therefore, we need this shell model. It's like a kabuk model. Shells are, I mean, each other. Therefore, these are the, I mean, where we get it from uh, atomic and molecular physics, actually. Therefore, it's like an atomic electron configuration. I mean, high stability at closed shell structures like noble gases in atom physics or chemistry, chemical properties determined by the valence electrons. Therefore, what we assume is ordered structure within a nucleus. Nucleons move independently in a potential well. Load energy stays determined by this mean field potential. You see, then we fill the nucleons, protons, and neutrons according to these magic numbers, and we obtain them. Therefore, the mean field potential between neutrons are always attractive, and for protons there are these Coulomb repulsion, and some of these two potentials are expressed by this Saxon form, or what is called Fermi function form. Now, what we do is basically we have these shells, like 1s, 1p, 1d, like in atomic physics, we fill them with protons and neutrons according to Pauli exclusion principle, and we see, and we obtain first three, look, 2, 8, 20, 2, 8, 20, then we cannot obtain the rest. Like same, if we use, instead of square well potential, we can use this harmonic oscillator potential and we obtain the same first three numbers, but the rest we cannot obtain. I mean, do you have any problems with this like shell configuration? Like, do you know the difference between 1s, 1s, or 1p, for example? S, P, D, F. These are states, you know. I mean, 1s is like a wave function of covering the full well, like this. 2s, number of nodes, 2 is you cross this line twice. Look, 1, 2. 3s is crossing this 3 times. 1, 2, 3. Therefore, why is it important? Because it's a wave function. When you have a wave function, psi, it describes, it has all the information of the nucleus or atom. Because when you say psi square, it is the probability of finding that particle in that volume. psi square. Therefore, if you look at the 1s, that's the ground state. It is fully occupied. Therefore, 100% is there. You see, if you look at the 2s psi square, it has yes, like 99% it is there because there is a gap here. So that you cannot find the nucleus there. That's the probability. It's not classical physics. It is quantum physics. Therefore, there is a probability of finding a particle in a volume. Now, what is the difference between 1s, 1p, and 1d? Okay, number of nodes, closest ones, but look, 1s is occupied the full, where 1p is like 30%, there is 70% is that. Therefore, this is like probability of finding a particle in that volume. This is the volume. If you have 1s, it is 100% is there. That's the probability is 1. 1p, it is like 30% is not there, 70% is there. Therefore, 1d, it is like 50-50. You see, that's the modern physics. Therefore, you should know such things very, very well. I mean, that's why then, I mean, we can produce any nuclei, any radioisotope theoretically or simulation when you do you run the experiment. Okay. I mean, if you have any questions, please.
Can I ask a question?
Yeah, please.
So, it's splitting of the wave function because of the angular momentum?
Of course. Yeah, I mean, if you look at the conserved quantities, angular momentum is one of them. Therefore, the total potential or effective potential has nuclear potential plus Coulomb plus centrifugal potential. That centrifugal potential is like a constant of a system. Therefore, L equals 0 is S state. L equals 1 P state. L equals 2 D states. So that you like build up a nucleus. When you say 1s, quantum number n is 1, s L equals 0. When you say 1 or 2d, n quantum number psi n and m. Okay, n is 2, L is SPD. 2. L equals 2. Okay. Therefore, this is like in modern physics, I mean atomic and nuclear and other physics, you don't have a classical view anymore. You have modern physics view. Therefore, you have a psi wave function. And psi is described by n, l, m, quantum numbers. And principal quantum number giving this 1, 2, 3, etc. Okay? It is n. And describes the orbital. L equals 0, S, L equals 1, P, L equals 2, D, etc. Okay, alphabetically it is going. And M is the orientation of it. Like 2L plus 1 times possibility. Therefore, it orients. You see, I will show you a little bit more. Therefore, shell model with this old mean field model, like Schrödinger equation, solving for this potential doesn't describe by using square wave or harmonic oscillator these numbers. Therefore, what we need is the spin orbit interaction, LS. You see, LS. Okay, when you say this LS, when you include it, like with the potential, like with Saxon together with spin orbit, you see, we get 2, 8, 20, 20, 50, 82, and all these magic numbers. Okay, and how do you build this nucleus? For example, when you have a carbon or uranium, what is the structure of, nickel, for example, aluminum? What is the spin? What is the parity? Because you see, when you have, when you have a gamma ray or electrons or photons, you should know where it comes from, so that what is the energy and whether it is allowed or not. Therefore, my father, I am from Kayseri, therefore we are very much linked with the money. Therefore, please take the first letters of this. Sen para diye sizden dur fakat para gelmedi. You build up to uranium, okay, no problem. Therefore, like you should be, I don't know how much you did, but we can practice it, okay? Keep it this in your mind and look at this, for example. Okay, you have 17 oxygen or 17 fluorine. Okay, what is the structure of this nucleus? These are mirror nuclei, almost same. What you do is send para diye. You see, like, do you know where 1/2 and 3.5 comes from? Yes, L plus S. Yes. Therefore, L equals 0, S is always minus plus 1/2. Therefore, when you have, for example, L equal 1 plus minus 1/2, it gives you 3.5 and 1.5. Okay, for P. That like you have this separation. P is P 3.5, 1.5. D 5.5 and 7.5, etc. It goes on. Okay. Therefore, you start by considering taking into account the Pauli exclusion principle. Okay. Two fermions can occupy the same level with different orientations. Therefore, two neutrons, you see here, it is the capacity, you see. 2 times 1/2 plus 1 gives you the capacity. Therefore, 1 plus 1, 2. 2 times 3.5 plus 1, that means 4. Okay, like this. 2 times 1.5 plus 1, 2. P orbital 6. D orbital 6, 10, etc. It goes on. We can practice it, okay? I mean, if you didn't understand. Therefore, what we do is we have 8 protons, 9 neutrons here. Put them here to, okay, these are neutrons, sorry. Yeah, 9. 2, 8, 9. Okay? And the others 2, 6, altogether 8. Therefore, this is the configuration for oxygen 16. If you have more, for example, 20 neutrons, 25, doesn't matter. You still keep including this. Therefore, this is the orbital that we have. Therefore, this is the angular momentum. Therefore, this is like 5.5 is the spin of this nucleus. Parity is calculated minus over L, minus 1 over L, eksi 1 üzeri L. Okay. L equals here 2. Minus over 2 is plus, therefore 5.5 plus. Same the other one. Therefore, you practice it, okay? I mean, if you have any questions, please ask me. These are your some other examples up to bismuth, lead, cerium, fluor, etc. These are the spin parities, and these are the homeworks for you. Okay. Now, this shell model accounts for magic numbers, ground state properties for almost all nuclei, some low-lying excited states, and pair effect. But it doesn't account, cannot explain the magnetic dipole and quadrupole moments, properties of excited states, ground states, spin types of nuclei with several valence electrons. We need another model. You see, I mean, then we move to collective model, what is called. It is a combination of liquid drop model plus shell model, so that we are able to explain not all, but some basic properties of nuclei. Hocam kaç dakika var?
Var da, canım biliyor. Çok biliyor. Onu geçiyor.
Okay. Now, regarding this collective models, I mean, it is like combining the features of shell model and liquid drop model. Now, the idea is, okay, this liquid drop model predicts spherical configuration in ground state for small deformations near equilibrium positions. Nuclei, I mean, protons and neutrons are not staying like constant, but it can be moving, or it can be rotating or vibrating. Therefore, vibrations are possible. Therefore, the idea is to solve Schrödinger equation for such cases. Now, we have this from electromagnetic theory. We have monopoles, dipoles, quadrupoles, and etc. Other moments. Now, when you have monopole, it's like, you know, breathing like this. Like this. Or when you have dipole, it shifts the center of motion. Okay, like this. But when you have quadrupole, the system completely changes because there are poles now, like Earth. You see, you either compress from the top or the side. Therefore, it starts vibrating or rotating. Like imagine on world, Earth, I mean, from the north and south poles, it is compressed. Okay, consider like this. When you have a charge distribution anywhere in the space, like a positive charge there, you have on the corner, you have an electric field towards outside, okay, if it is positive. If it is negative, then from inner side, you have electric field. Now, therefore, the presence of electric charge creates electric fields. Now, when you have this compression from top, like Earth, then this charges polarize, and they create this center of mass and they start rotating. When you have rotating or moving charge, then you have magnetic field. You see, you don't have some electric field, but also magnetic field. That's why we have moments like electric moments and magnetic moments, like this. Therefore, all nuclei creating us are either prorate or oblate. They are not spherical, you know that. For exception, few of them, no nucleus are spherical. Most of them either oblate, that's deformed, negatively deformed, and polarized by the top, or from the side. Therefore, this is like basics of nuclear structure, but you should know this rotation or vibration states. And these are the energy levels for example, hafnium. You see, this is ground state, first excited state, second, etc. It's continuing. This is spin parity. And when you have a gamma ray from here to ground state, therefore there's this gamma rays with this energy. That's rotational band, and mostly very, very close to the moment of inertia, and the energy of that state is Jj plus 1 over y, moment of inertia. Therefore, these are basics, basically, I mean, but you should know.
Off-plate elements are more exact than others.
Yeah, I mean, yes, I mean, because this is the easy form. I mean, mostly of the structure polarized because the charges are on the poles, so that it starts rotating. Yes, but we also observe such structures. It's not very common, but yes, we also observe that. Therefore, such structures mostly present rotational structure, whereas the other one is mostly vibration states. Yeah, it is vibrating inside, so that it is an extra structural properties. Now, this is
Measure the experimental rotation states is through scattering experiments,
yes, well, all
and you can
Yes.
find out these rotation states.
yes, we do. Yeah, I mean, from electron scattering experiments. Normally, I mean, the way to examine a structure is, for example, if you would like to examine this, therefore, we should look at that. Through light, yes, we see this, this is scattering of light from here, this one, therefore, we can see it, and we describe. Therefore, in order to examine a nucleus or nuclei, we shouldn't harm it or deform it. Therefore, that's why we use electrons mostly, so that we, without deforming the structure of nucleus, we observe its characteristics. Sorry. Okay, I can shift to reaction or what's the time now, hocam?
Onu geçiyor. İstersen istersen. Yani da ara verelim diye. Hani
İsterseniz bir ara verelim. Yani sonra şeye devam edelim.
çağ
Okay, let's.
Evet.
O zaman devam edebiliriz. Okay. Well, if you feel tired, yani yorgun hissediyorsanız şey yapabiliriz. Okay. We have a 5 minutes break.